Welcome week 12 to computational quantum chemistry. So, this will be the last week of this course. So, we are going to cover three special topics: simulation of nuclear magnetic resonance, NMR spectroscopy, take care of the relativistic effect in the calculation, and complete active space or CAS-SCF based method if you are interested in certain excited state or are working with transition metals. Now, we will start with nuclear magnetic resonance. This is one of the commonly used spectroscopic tool by chemists, and so the nuclear magnetic resonance is a spectroscopic technique based on the transition between nuclear state of certain atoms, and the energy difference between the state is induced by an external magnetic field. So, you need heavy magnets to do this kind of spectroscopy. Electromagnetic radiation in the radio frequency range facilitate these transitions, and the absorbed frequency of the nuclei varies due to the nuclear shielding, an effect caused by the surrounding electrons that modified the magnetic field at the nucleus, usually lowering it. Nuclei only with an odd spin magnetic moment exhibit splitting in the presence of an external magnetic field. Usually nuclei with half spin is preferred as it gives you two state after splitting. So, you have proton NMR or hydrogen NMR, 13C NMR, 15N NMR, 19F NMR, 31P NMR. So, each of these cases where the nuclei have a half spin is preferred, and of course, the proton NMR is the most popular. Now, what is chemical shift? The chemical shift refers to the variation in NMR resonance frequency due to the difference in the local electronic environment of a nucleus. It is measured in parts per million relative to a reference compound. Example, trimethylsilane for 1H, the proton NMR or 13C NMR. And the frequency shift is generally calculated as frequency of the signal, frequency of the reference by spectrometer frequency in 10 to the power 6, and the electron shielding and deshielding affects the chemical shifts. Shielded nuclear explain lower shifts, while deshielded nuclear have higher shifts. Now, functional groups and molecular structure influence chemical shift, making them useful for identifying molecular compositions, and TMS is generally most common compound in the NMR reference, and that is considered as the shift to be 0. Now, of course, solvent, temperature, molecular interaction can also affect the observed chemical shift. Because the chemical environment affects the chemical shift, from the NMR spectroscope you can actually get a lot of information about the structure of the molecule. That is why it is a very popular tool. Like in the Department of Chemistry, IIT Bombay, the NMR machines run 24 hours a day, 365 days in a year, because a lot of the people need to take these NMR data to get what kind of compounds they are doing. So, sometimes it is important to simulate this spectra, so which gives you a good correlation between the structure of the compound and the measured NMR data. Remember, one of the major aim of computational quantum chemistry is to interpret experiments. So, if you see the simulated values and look at your experimental values, and then you can get the structure of the molecule, and you can actually modify the structure, recalculate the values, and if you see that is it matching with the experimental values better or not, by that you can guess an idea about the actual structure. So, let us do our calculation. We are going to take a very simple molecule, and that is isotropic shielding of 13C nucleus of propionic acid in CHCl3 solution, and this is how the input file looks like. One of the important thing is to use gauge independent atomic orbitals, because the magnetic gauge may not be properly described in a finite basis set otherwise. So, what happens is that because of the gauge dependence, the results become very sensitive with the size of the basis set. So, small basis set calculation can give you very bad numbers unless you are using gauge independent atomic orbitals, and ORCA by default uses the gauge independent atomic orbital. The meta GGA functional is generally a good option for predicting the NMR constant, and the gauge independent variant of the approach by Dobson is recommended. So, you see this tau or dog is equal to Dobson, and generally it is a good idea to use triple zeta quality basis set. So, PCSS EG2 or def2TZ VP, but because I want to do the calculation fast here, I want to do the calculation in using a smaller basis set, and these are the experimental values of the shift which are available. So, let us do the calculation. So let me copy the input file. So this propionic acid.xyz can be find out from this link. You can optimize it yourself also. So let me save the input file. Propionic acid .inp. I did not put a proper name, so let me first rename it. Let me run it. So let me open an Excel file where I can So this is the isotopic chemical shifts, and these are the two values you are getting. So let me copy these values. So this is the three values. So just calculating this is not good enough. What we need to have is to calculate the chemical shift. Now, how you calculate the chemical shift? You can have two options. One option is that you can actually calculate the value of the TMS, or what you can do is that you can actually use the shift from one of the known values. So, among the compounds of the NMR spectra taken for a compound, it may be happen that you are sure about one of the peaks, that this peak correspond to this one. So, you can match that particular peak with the experiment, the calculated value of that particular peak with the experiment, and take the shift as subtract the shift from the other peaks also to get a value of the corresponding shift. Or what you can do is that you can actually calculate the value of the TMS and use that shift. So, we are going to use the value of the TMS. The TMS geometry is actually given in this GitHub link. So, let me save as tms.inp. So, these are the isotopic shift for the 3 carbons. Now, you can see that the shifts are actually slightly different. So, you may think that how it is possible. One of the reasons it may be that due to the numerical problem. So, what you have given the geometry may not be perfectly symmetric. So, this can give you this kind of small variation. A good idea will be to just average them over. So, I can put them together. Sum them up. by 4. So, this is the value for the TMS. Now, I can calculate the shift. Okay, maybe I should put a row above. So, the shift will be all of them has to be 11. So, it is 11, 29, 177. If we go and see the experimental values given, it is 8, 27, 181, and the results will look slightly better if you go to a triple zeta basis set. You can do it yourself, that calculation. So, this way you have seen how to calculate the NMR shift. It will be a good idea if you do a few more examples, try few more examples yourself and try to convince it. One of the things which is important is that one of the reasons it may not match, the calculated value may not match with the experimental value, because you are doing with one single conformer. Now, the experimental molecule can be a linear combination of multiple conformers. So, you need to do some kind of a Boltzmann averaging, and you can see the literature how to do the Boltzmann averaging. You can search in the internet to get proper agreement with the corresponding experimental value.